So, you want to know what oil is, or where it comes from, how it's made. Scientifically named petroleum, colloquially named oil or fossil fuels, intended to create the idea or image that the substance that we run nearly every aspect of our lives is from dead plants and dinosaurs. However, this does not explain how dead plants and animals can form large underground reserves of oil. For instance, the biggest oil field in the world, the Ghawar oil field in Saudi Arabia, has produced more than 65 billion barrels of oil and is estimated to have a remaining 58 billion barrels of oil equivalent still in place. At 42 gallons per barrel, this is the equivalent of slightly more than 5 trillion gallons of oil in a single reservoir. To put that into perspective, that is slightly less than the estimated 8 trillion gallons of water that are at Lake Mead. In addition to its nearly unimaginable size, some of these oil reservoirs are pressurized and form an oil spout when punctured. Unless dinosaurs and algae stampeded into a sinkhole just like this for thousands of years, how does the current model of petroleum generation make any sense at all? Let's see what the experts have to say. According to geologists and petroleum experts, oil is formed when both phytoplankton and zooplankton, as well as algae and bacteria, sink to the bottom of an ancient ocean or lake and mix with inorganic clay-like materials that enter these oceans from streams and rivers. This creates an organic-rich mud. This mud can only form in still water environments. This mud cannot be exposed to too much oxygen, or else the organic matter in the mud would be decomposed by bacteria and disappear quickly. Therefore, environments where oil form are known as anoxic environments. And before this organic matter is destroyed, it is buried by more sediment and lithifies to become sedimentary rock, creating organic shale. Shale is a fine-grained sedimentary rock that is formed when silt and clay are compressed. It is composed of many thin layers, and it readily splits into thin pieces where these layers meet, making it a relatively brittle stone. Shale is composed of small grains and various minerals along with organic particles. Shale forms when layers of silt and mud collect and lithify. Lithification is a process where freshly deposited loose grains of sediment compact and form a rock layer. For instance, sand lithifies into sandstone. Mud lithifies into mudstone. Calcium carbonate from sea creatures lithifies to limestone, and so on and so forth. If the shale is buried between 2 and 4 kilometers, its temperature increases due to its location in the Earth's interior. This increasing pressure and temperature of the shale transforms into a waxy material known as kerogen. Shale that contains this material is known as oil shale. If temperature of the kerogen are greater than 90 degrees Celsius but lower than 160 degrees Celsius, kerogen is transformed into oil and natural gas. At temperature higher than this, only natural gas or graphite is formed. This temperature range is known as the oil window. Upon heating, kerogen converts in part to liquid and gaseous hydrocarbons. Petroleum and natural gases form from kerogen. The composition of petroleum and natural gas are mixtures of hydrocarbons. On average, they consist of 85% carbon, 13% hydrogen, and 2% of nitrogen, sulfur, and oxygen. Here are some of the variations of hydrocarbons, and most people would be familiar with at least some of these names. The transformation from organic material to oil depends on the classification of source rock. Source rock is a rock which has generated hydrocarbons or which could generate hydrocarbons. Source rocks are one of the necessary elements of a working petroleum system. Source rocks are classified from the types of kerogen that they contain, which in turn governs the type of hydrocarbons that will be generated. Type 1 source rocks are formed from algal remains deposited under anoxic conditions in deep lakes. They tend to generate waxy crude oils when submitted to thermal stress during deep burial. Type 2 source rocks are formed from marine plankton and bacterial remains preserved under anoxic conditions in marine environments. They produce both oil and gas when thermally cracked during deep burial. Type 3 source rocks are formed from terrestrial plant matter that has been decomposed by bacteria and fungi under oxic or suboxic conditions. They tend to generate mostly gas with associated light oils when thermally cracked during deep burial. Most coals and coaly shales are generally type 3 source rocks. In other words, the contributing factors to the type of oil that is produced by a source rock includes but not limited to freshwater versus seawater, zooplankton versus phytoplankton, and terrestrial plant life. Still, the oil has not reached its destination. For that, petroleum geologists use the idea of hydrocarbon migration. The migration of hydrocarbons is a little understood but critical process of the petroleum system. The short definition is movement of petroleum from source rock toward a reservoir or seep. Pearl is lighter than water, so as it escapes from the source rock, it rises through pores in rocks, displacing water. Rock bodies that contain significant amounts of oil are known as reservoir rocks. For the oil to remain trapped in the reservoir, there must be some sort of thick, impermeable layer of rock to seal the reservoir. If this seal exists, then oil, gas, and water are trapped beneath and can be drilled in to obtain the oil. It is admitted by petroleum geologists that there is a problem with the theory of petroleum migration when the pressure required for reverse osmosis shrinks the pore holes of the source rock and preventing migration. Here's an excerpt from a lecture that explains what I'm talking about.
Okay, now I said, all right, so when you compact things, then grains get closer and closer together. And that means that the doorways, the pathways to escape for the molecules become smaller and smaller. So, right, and so the more I go down in depth, the more the pore diameter decreases, and the more difficult it becomes for these molecules to migrate through between the pores. Now, this, in fact, is the pore diameter. So I said the pore diameter is like this room, and that's the pore throat. And the pore throat is about 10 times on average smaller, on average. That's where the molecules have to go through. It's fine to move within the pore, but eventually, in migration, they have to go through the pore throats up out of the source rock. And so if you decrease this here by a factor of 10, you'll get a curve that is, instead of 25 here, it'll be 2.5. So the curve for the pore throats would be like this here, a very steep curve, and you'd see that most of these molecules won't be able to migrate out. And so this is why, I say this migration process is very, very poorly understood. We really don't know very well how these things can migrate out of these rocks. And so this is the controversy. Oil is generated at temperatures of 60 to 120 degrees, which are typically found at depths of 2 to 4 kilometers. But the source rocks at those depths are so compacted that their permeability is too low for efficient primary migration. Now I say permeability, but I could also say the pore throats, because the permeability depends on the pore throats.
With that being said, the theory of hydrocarbon migration just doesn't hold water. It does, however, make sense with the practice of hydraulic fracturing, also known as fracking, the well stimulation technique involving the fracturing of bedrock formations by a pressurized liquid. The process involves the high pressure injection of a fracking fluid, primarily water containing sand or other proppants suspended with the aid of thickening agents, into a wellbore to create cracks into the deep rock formations through which natural gas, petroleum, and brine will flow more freely. In other words, hydraulic fracturing is the migration theory in practice. However, with the aid of human intervention, not through the mechanisms of tectonic forces in natural formations. There is, however, a different theory as to the creation of petroleum, which is called abiogenic petroleum origin. It's a body of hypotheses which propose that petroleum and natural gas deposits are mostly formed by inorganic means rather than by the decomposition of organisms. Thomas Gold's deep gas hypothesis states that some natural gas deposits were formed out of hydrocarbons deep in the Earth's mantle. Theories explaining the origin of petroleum as abiotic are generally not well accepted by the scientific community and are rejected by most researchers and scientific theories on the subject. In 1951, the Soviet geologist Nikolai Alexandrovich Kudryavtsev proposed the modern abiotic hypothesis of petroleum. On the basis of his analysis of the Athabasca oil sands in Alberta, Canada, he concluded that no source rocks could form the enormous volume of hydrocarbons and therefore offered abiotic deep petroleum as the most plausible explanation. Humic coals have since been proposed for the source rocks. Unfortunately, abiogenic petroleum still relies on the faulty migration theory. At this time, I would like to point out that the transformation from organic material to hydrocarbons is very similar to the fermentation process. Fermentation is a number of metabolic processes that produces chemical changes in organic substrates through the action of enzymes. In biochemistry, it is narrowly defined as the extraction of energy from carbohydrates in the absence of oxygen. So essentially, with the addition of pressure and heat, the fermentation of carbon-based life forms leads to the production of kerogen and hydrocarbons. This idea also parallels petrifaction or petrification. It is the process by which organic material becomes a fossil through the replacement of original material and the filling of the original pore spaces with minerals. Petrified wood typifies this process, but all organisms from bacteria to vertebrates can become petrified. As with all petrification processes, instead of a waxy kerogen hydrocarbon-like substance, fossils remain. Fossils created through the process of permineralization tend to contain a large amount of the original material of the specimen. This process occurs when groundwater containing dissolved minerals fills pore spaces in cavities of specimens, particularly bone, shell, or wood. The pores of these organisms' tissues are filled when these minerals precipitate out of the water. Permineralization process can result in some astounding displays of agates. When placed under a microscope and lighted, oftentimes the cellular structure of the specimens are preserved. Agate is a common rock formation consisting of chalcedony and quartz as its primary components. Both silica or silicon dioxide based rocks. The exact process of petrifaction was unknown until a man named George Beck made an important discovery. He was the co-discoverer of the petrified forests of central Washington and largely responsible for the establishment of Ginkgo Petrified Forest State Park in Vantage, Washington. With close proximity to the Yellowstone supervolcano, it should be no mystery as to how the elements of volcanic activity contributing copious amounts of silica to the environment fit into this story. It was here at Ginkgo Petrified Forest State Park where George Beck made an important discovery detailing one of the processes of the formations of petrified wood. There was a nearly unanimous occurrence of these petrified wood specimens being found not only in the vicinity of pillow lava, but literally being pulled from within the formations of pillow lava. Pillow lavas are lavas that contain characteristic pillow-shaped structures that are attributed to the extrusion of the lava underwater, or subaqueous extrusion. Pillow lavas in volcanic rock are characterized by thick sequences of discontinuous pillow-shaped masses, commonly up to 1 meter in diameter. They occur wherever lava is extruded underwater, such as along marine hotspot volcano chains and the constructive plate boundaries of mid-ocean ridges. Scientists have even captured the creation of pillow lava underwater. Therefore, we have all of the elements of the petrification process locked into one geological location, removing the mystery of at least one of the processes of formation. This evidence is also supported by the process of artificial petrifaction. In 2005, scientists at the Pacific Northwest National Laboratory reported that they had successfully petrified wood samples artificially, infiltrated samples in acidic solutions, diffused them internally with titanium and carbon, and fired them in a high-temperature oven, approximately 1400 degrees Celsius, in an inert atmosphere to yield a man-made ceramic matrix composite of titanium carbide and silicon carbide, still showing the initial structure of the wood. Fulton Hicks of Greenwich, Connecticut, received a patent for his recipe for rapid artificial petrification of wood under U.S. Patent 4,600,012-050 in 1986. Hicks' recipe consists of highly mineralized water in a sodium silicate solution combined with a dilute acid with a pH of 4.0 to 5.5. Samples of wood are penetrated with this mineral solution through repeated submersion and applications of the solution. Wood treated in this fashion is, according to the claims in the patent, incapable of being burned and acquires the features of petrified wood. So, to recap, petrified wood has been recreated through artificial means in environments of high heat, acidic pH, and an anoxic environment, mimicking the silica-rich, anoxic, high-heat environments that would be found in the vicinity of volcanic eruptions. You're probably wondering, what does petrifaction have to do with the creation of oil? Well, the point is, there are three potential outcomes for trees, plants, animals, algae, and that is petrifaction, or becoming a fossil, fermentation and becoming oil, or decomposition, leading to participation in the nitrogen cycle, resulting in dirt or soil. Maybe if we can date the oil reserves, this will help us arrive at a conclusion of their origin. Instead of going through a drawn-out lesson of how radiometric dating works, here's the abridged version. Carbon-14 dating measures the decay of the carbon-14 isotope. Because the half-life of carbon-14 is 5,700 years, give or take 30 years, the total lifespan of a carbon-14 molecule is no more than 57,000 years. Upon reaching approximately 57,000 years, the carbon-14 decays into nitrogen-14. Living organisms contain a 1-to-1 ratio of carbon-14 to carbon-12. But upon death of a living organism, it will cease to absorb any more carbon-14 data. So comparing the ratios of a fossil or specimen will render a significantly accurate dating of that specimen. That is how a significantly accurate dating of living organisms, or the remains of living organisms less than 57,000 years old, can be dated. When older fossils, for example dinosaurs, are found, there is insufficient carbon-14 to retrieve a date, and that is an indication that the specimen is older than 57,000 years old. Fortunately, carbon-14 dating does not work on oil, but that does help to deduce that all oil reserves are older than 57,000 years old. In 1994, a research team headed by J. Michael Muldoon developed a potential method of dating oil fields. Their dating system measures the relative amount of organic compound oleanine in the oil. Oleanine is highly associated with angiosperms, flowering plants that have evolved and spread since the early Cretaceous. Many flowering plants produce derivatives of oleanine called oleanoids that are toxic to predators. Because angiosperms became more plentiful as time progresses, younger organic deposits that are converted into oil are likely to contain more angiosperms. Because the geological processes involved convert the oleinoids in the angiosperms into oleanane, the more oleanane found in a given oil sample, the more recent it is likely to be. The method is not a very precise yardstick. Oils of any age can lack oleanane if flowering plants were not part of the material from which it formed. But lack of oleanane is a significant clue that oil may have been formed in the Jurassic or older times, before angiosperms evolved. If the compound is present in relatively small amounts, the crude is almost certainly Cretaceous or younger. If it contains large amounts of the organic substance, on the other hand, its pedigree most likely dates from the post-Cretaceous or Tertiary age, 65 million to 5 million years ago. The researchers did get a surprise, however, when they analyzed a 307-million-year-old concretion associated with Pennsylvanian age coal seam in Illinois. Despite the fact that this coal ball dates to well before the period when flowering plants first came on the scene, they found measurable levels of oleanine. In other words, the oleanane dating method is relying on compounds created by plants millions, if not hundreds of millions of years ago. So, supporters of the abiogenic hypothesis generally reject the supposition that certain molecules found within petroleum, known as biomarkers, are indicative of the biological origin of petroleum. They contend that these molecules mostly come from microbes feeding on petroleum in its upward migration through the crust. That some of them are found in meteorites which have presumably never contacted living material, and that some can be generated abiogenically by plausible reactions in petroleum. So because we can't date the oil, geologists attempt to date the bedrock or the source rock or any surrounding rock and remains in the areas of things such as the Athabasca oil sands, estimated to be about 110 million years old, or the Gawar oil fields, believed to be of the Jurassic period, 200 to 150 million years old. And lastly, the Orinoco oil belt in Venezuela, estimated to be about 25 to 50 million years old. These are three of the largest oil reserves on the planet. The La Brea tar pits are a good example, at least, of knowing how young an oil field is not, based upon the fact that radiocarbon dating of a camel fossil rendered a 41,000-year-old date, assuming that that camel was not placed in the location of the tar pit prior to the tar pit's creation. So if we cannot use radiometric dating on oil or an oil field, maybe we can use radiometric dating on petrified wood. There are several isotope pairings that are used in the radiometric dating process. However, the one that we're going to focus on is uranium to lead dating, abbreviated U to PB. It is one of the oldest and most refined of the radiometric dating schemes. It can be used to date rocks that formed and crystallized from about 1 million years to over 4.5 billion years ago, with routine precisions in the 0.1 to 1% range. Uranium-238 naturally decays through a series of daughter products that are each and all radioactive through beta and alpha decay until lead-206. Lead-206 is stable, the final daughter product of the uranium-238 decay chain. Minerals that include uranium will slowly acquire lead as uranium decays. One of the more prominent applications of uranium to lead dating is applied to zircon. The mineral incorporates uranium and thorium atoms into its crystal structure, but strongly rejects lead when forming. As a result, newly formed zircon deposits will contain no lead, meaning that any lead found in the mineral is radiogenic, Since the exact rate at which uranium decays into lead is known, the current ratio of lead to uranium in a sample of the mineral can be used to reliably determine its age. In the case of metamorphic rocks, meaning rocks that arise from the transformation of existing rock to new types of rocks in a process called metamorphism, the original rock is subjected to temperatures greater than 150 to 200 degrees Celsius and often elevated pressure of 100 megapascals or more, causing profound physical and chemical changes. Dating of zirconium in metamorphic types of rocks such as granite can obtain a reliable measure of the rock's age. Sedimentary rocks are types of rocks that are formed by the accumulation or deposition of mineral or organic particles at Earth's surface, followed by cementation. Radiometric dating of sedimentary rock is unreliable because, in effect, the only dates that will be achieved is date of the individual particles within the sediment's creation, not the actual amalgamation or cementation of the sedimentary rock itself. A good example of attempting to use radiometric dating on sedimentary rock would be the same thing as attempting to date a cake. The dates obtained from each individual component of the recipe involved in creating cake, such as sugar, flour, eggs, could yield a date as old as 3 years old obtained from a sugar molecule, 30 days obtained from a flour molecule, and 7 days obtained from parts of the egg, when in fact the cake was baked just yesterday. This is a principle called observance, or observation. In the case of igneous rock or magmatic rock, igneous rock is formed through the cooling and solidification of magma or lava. In fact, igneous rock is a prime example of rock that fulfills the requirement of the observance property. Unfortunately, radiometric dating falls short of providing accurate information pertaining to igneous rocks. In the case of Mount St. Helens, the 1986 dacite lava flow was observed by the human eye. However, when potassium-argon dating methods were applied, the lab results of radiometric dating conducted in 1996 on the Mount St. Helens 1986 dacite lava flow, variance in ages from 350,000 years to 2.8 million years old were obtained from a rock that was observed to be only 10 years old. And it turns out that these readings were not an anomaly, because across the spectrum of human existence, with other volcanoes that were observed to have erupted, the same result of inconsistent radiometric dating on observed and recorded lava flows was obtained. The faults of radiometric dating has 3 crucial assumptions. Assumption 1, all the daughter atoms derived from parent atoms. Assumption 2, no other processes has affected the parent-daughter relationship. And assumption 3, constant decay rates. The condition that is exhibited in the Mount St. Helens dating anomalies, as well as the other volcanic anomalies from around the world, is inheritance. And that is that at the creation of the igneous rock, external elements were inherited by the rock. So understanding the inheritance principle, radiometric dating is unreliable when applied to petrified wood, because the permineralization process involves the depositing of external minerals. So if the proposed age of the ginkgo petrified forest of 15.5 million years is incorrect, what exactly do scientists know about the phenomena that is petrified wood and the area of the ginkgo petrified forest? Without delving too much into stratigraphy, the study of layers of rocks, the law of superposition, in its plainest form, it states that in undeformed stratigraphic sequences, the oldest strata will lie at the bottom of the sequence, while newer material stacks upon the surface to form new deposits over time. Paleontologists and paleobotanists use this sequencing to identify the relative ages of any fossils found within the strata. Here's an explanation of the geology behind the discovery of petrified wood.
This is the last of the German chocolate cake that was gifted about a week ago. Okay, so why am I showing you this? The German chocolate cake is a wonderful analogy to talk about all these flood basalts. And the maximum thickness is what? 3 miles thick in places. At Vantage, the German chocolate cake is about half that, maybe 1.5 miles, something like that. Maybe even less, I kind of forget. Doesn't matter. I've done something with the inside of this cake. So what do you suppose I'm trying to show you inside of this German chocolate cake? What are the toothpicks all about? That's correct. These toothpicks are the petrified logs. There's only one major place in the German chocolate cake where the petrified logs that I just showed you, and we'll show you a few more samples coming in a bit, are coming from. One horizon. Now you remember, there are 300 layers in this German chocolate cake. 300 brown layers. And there's only a couple of other horizons in the cake where there's a little bit of petrified wood. But for our purposes tonight, we're going to just focus on one horizon. And I want you to look as carefully as possible at a couple of things. First of all, the non-chocolate layers are sediment horizons for us. You can think of as sandstones if you want, or lake beds. That's fine. Either one of those is fine. And so notice that I don't have our petrified logs in the lake bed or in the sandstone. So I'm introducing a couple new concepts now. The main concept I'm introducing is that we still don't have precise dates on each lava flow in the German chocolate cake, but especially where we have sediment horizons, sandstones or lake beds, we probably have thousands and thousands of years of quiet after one eruption of basalt lava and before the next one. And so we really have, when you look at these kind of blonde layers, time capsules. A whole ecosystem got established. Thousands and thousands of years, maybe 10,000 years, maybe more. That's a long time.
What the professor is saying is that the estimated 300 layers of the Columbia River basalt group seen here, pictured in the map, that when we find petrified wood samples, they are not located buried in the sedimentary layers, as seen here, or in the basalt layers, seen here. By the way, this is a picture. The title reads, Horizontal Volcanic Basalt Still Intruded Above Sedimentary Rock Layer. That the petrified wood samples are residing on top of this sedimentary layer and below in the basalt layer. The reference to the amount of time or the creation of ecosystems is in reference to this sedimentary layer here, either deposited during long stretches of times by factors such as erosion and water runoff, or suddenly and all at once. The idea of catastrophism theorizes that the Earth has largely been shaped by sudden, short-lived, violent events, possibly worldwide in scope. Proponents of catastrophism propose that each geological epoch ended with violent and sudden natural catastrophes, such as major floods and the rapid formation of major mountain chains. Plants and animals living in parts of the world where such events occurred became extinct, to be replaced abruptly by the new forms whose fossils defined the geological strata. In the same conditions of singular events leading to the creation of petrified wood can be seen all over the world. For example, the Gilboa fossil forest in New York is estimated to have occurred roughly 380 million years ago, containing fossils of what is thought to be the first trees on planet Earth, morphologically different from the fossils found at Jamorillo Petrified National Forest Park in Argentina, with the species Araucaria mirabilis, an ancient relative of contemporary evergreen conifers, and Ginkgo Petrified Forest State Park, containing species such as redwood, walnut, Douglas fir, elm, maple, and many other common trees. The types of fossils found help to identify the chronology in the different sets of strata that are laid across the planet. So the idea that I would like to have carry over into the production of oil taken from the petrified wood process would be the idea of catastrophism leading to the creation of such oil fields. Finding fossils is really all about knowing where to look, how to identify the landscape, and find all the components that are necessary for the creation of a fossil. Marine environments are an ideal place for finding fossils because of the likelihood of volcanic activity and because the water provides an anoxic environment. However, for terrestrial life, the likelihood of organisms remains resulting in a fossil are rather low, likely to be within the fractions of a percent range. Yet it is still clear from the fossilized remains of Pompeii that catastrophism plays an important role in the fossilization process. In 1986, scientists were able to observe the carnage from a volcanic explosion in Mount St. Helens, and what you're looking at is trees being washed downstream. And while the Uttarakhand glacier burst in 2021 that resulted in a flood is just a fraction of what a proglacial flood would look like, we can still get an idea for the power of catastrophic flooding. It should be clear that the devastation caused by the Mount St. Helens eruption could contribute a massive amount of organic material. However, the likelihood of it all ending up at a single place and also being quickly buried and fermented in an anoxic environment are slim to none. So as opposed to the idea of many trees contributing to the creation of oil fields, I propose that just one tree was the contributor to the creation of an oil field. The structure that was pictured is known as Devil's Tower. It is a butte, possibly laccolith, composed of igneous rock in the Black Hills section of northeastern Wyoming. It stands 867 feet from summit to base. The current belief is that Devil's Tower was formed by a magma intrusion. An igneous intrusion occurs when magma solidifies before it breaks through the Earth's crust. As the continents shifted and water eroded away the sedimentary layers, the solidified magma was exposed. Geologists believe that while Devil's Tower formed from cooling magma 50 million years ago during the Eocene epoch, it was not exposed until 1 to 2 million years ago. Potassium-argon dating, as well as argon-40 to argon-39 dating of structures in the area as well as Devil's Tower, indicate an age of anywhere between 55 to 49 million years ago. However, we know from the Mount St. Helens 1986 dacite lava flow, with tests conducted on 10-year samples, that ages as old as 2.8 million years were indicated. And this is the problem of inheritance. First, let me clarify that I am not the first person to propose that Devil's Tower is an ancient tree stump. And I also want to be clear that the whole ideas about the shape of the earth are not my concern in this video. Here I am strictly talking about the plausible occurrence of ancient petrified tree stumps. And the first claim of opposition is that tree stumps don't look like Devil's Tower, and Devil's Tower does not look like a tree stump. The second claim is that petrified tree stumps do not take on the properties that Devil's Tower does. The third claim would be that plants, or tree stumps in this case, do not exhibit the columnar jointing that is found on the surface of these sites. This picture of a neighboring formation called Devil's Postpile. Yet here we have cross-sections of Triassic petrified wood on the right and a modern pine on the left. The fourth claim is kind of odd because in previous videos discussing ancient tree stumps, many people proposed the idea that trees were once silica-based life forms as opposed to carbon-based life forms. But earlier in this video, we detailed the process of silicification. In other words, a petrification process in which silica-rich fluids seep into voids of earth materials, rocks, wood, bones, and replace the original materials with silica. And opposition claims that this has nothing to do or zero connection with the fact that basalt, the proposed form of extrusive igneous rock, has silica content. The next feature I want to call to attention is the Jugurtha tableland of Tunisia. Nearly 1 mile long, a third of a mile wide, and 2,000 feet tall, Jugurtha tableland is a geologic feature known as an inverted relief. Millions of years ago, the hard limestone top of a mesa was actually the bottom of a valley. Over the years, the softer surrounding hills were worn away by erosion, leaving the tableland as the highest point on the plain. It is important to note that limestone can only be created by the death and layering of marine crustaceans contributing the necessary calcium carbonate from their shells to create the limestone. And while Jugurtha's table certainly does resemble something looking like a fish, it's hard to imagine that Jugurtha's table and its sister structure up here were once the bottom of a valley. As with Devil's Tower, opposition will claim this looks nothing like a tree stump, and while I'll admit that its odd shape certainly doesn't resemble the uniform circular fashion of a traditional tree stump, I will have to add that nature itself is not uniform, and sometimes randomness is the predominant feature. And certainly not all trees are perfectly circular. And while Jugurtha's table is a limestone feature, it may not fit the category of silicification. However, after silica, calcium carbonate, chemical name for limestone, is the most common form of wood petrification. There are countless other features around the world that can fall into the hypothesis of ancient tree stumps, such as Mount Connor in Australia, Mount Roraima on the border of Venezuela and Brazil, the Brown Bluff feature in Antarctica. But really, the amazing thing is what we don't know about the petrifaction process and just how quickly it can happen. Here's a presentation by Peter Jupp at the Thunderbolts Project website discussing the potential role that electricity plays in one of the possible formulas of petrifaction.
The conversion of the wood to rock, while again demonstrates the creation of fulgurites by a powerful electric discharge. Yeah. There we go. We're right there in that light. Keep right there. What is this wall?
This is fulgurite. It's fused silica, which follows the path of the lightning or electrical discharge.
Was this how these trees were petrified? Further evidence comes from Canada. E.R. Milton describes his examination
of a petrified tree trunk in Alberta. The piece was pure, clean silica inside. It was coated with a rough, opaque crust of partially fused sand. The tree whose stump was petrified was alive 5 years ago. After the tree was cut down to accommodate the right-of-way for a new power transmission line, an accidental break allowed the live high voltage wire to contact several tree stumps in the ground. The power was cut off within hours of the break. All of the tree roots which contacted the broken wire were fossilized. Obviously, electricity can metamorphosize matter quickly. Look at this. Around about
This is
60,
Lesbos
70
again.
foot long, solid rock, but
Just
clearly
amazing.
a tree. See how this is actually still wood, part of it, but otherwise it's been turned to rock. A substance a bit like marble.
So I wonder, is this feature here on the island of Lesbos columnar jointing from a basalt lava flow? Or is it one of the remaining petrified tree stumps as a result of catastrophism? Or possibly the result of an ancient planetary war with unknown advanced weapons? At the end of the day, geologists are constantly learning new things. For example, before the eruption of Mount St. Helens, it was believed that all volcanoes erupted upwards. Here's an aerial view of the peak of Mount St. Helens. And afterwards, the sideways eruption, the area that it devastated. As far as I'm concerned, there are no doubts about it. I'm more intrigued by who cut them down and how, as opposed to whether or not these really are ancient tree stumps that led to the deposition of organic matter that was required for the natural production of oil fields. But when everything is said and done, I wouldn't be surprised if some of these natural formations occurred inside of a few 100,000 years ago.